Start the recording. Okay. Okay, so this is first half an hour. In principle, is to answer questions about yesterday's talks. But any point you want to raise, in addition to what we already said yesterday, is welcome. We can't hear you, Valerie.
So I guess,
yeah, please.
Bit of a fairly broad question for, sorry, Mike. I went to another room to so I can ask quietly away from my kid, and they followed me. 1 second. Let me try here. Okay, so yeah, it's very interesting that Carlos talked about this maximum reheating temperature and effective using gravitational waves. So I was thinking, like, do we know if someone threw $1 billion at you, what sort of bound could we get on an effective, either from a cosmic variance limit CMB experiment, or from for like greatly improving understanding of, like, I guess, photon capture and deuterium cross sections and the deuterium abundances through astrophysics also. Do you have any idea? Because I imagine if you get to 10 to minus 6, you're getting really serious, like into leptogenesis relevant regions, like 10 to the 13 sort of temperature as the maximum reheating.
That's a nice point, yeah. Well, in Big Bang nucleosynthesis, as you were mentioning, deuterium abundance, indeed the precision is not as good yet. No, for instance, I was thinking of inhomogeneous Big Bang nucleosynthesis, and there you still have some liber arm, which means that it could happen that the number of relativistic degrees of freedom is different in different patches, and still you can get the helium abundance that we observe and the deuterium abundance we observe today nearby. So it's not easy to put strong constraints on the number of effective degrees of freedom at, say, 1 MeV. If you want to go all the way up to 10 to 13 GeV, that's even worse. You want to know whether there's Rajana neutrinos up there, no? So it's more complicated. I guess unless you have something like primordial black holes, which gives you a clue onto what's a typical mass that collapses when a large fluctuation re-enters the horizon, and you see the mass distribution of those black holes. Unless you get there, it's very difficult to have any handle on how many degrees of freedom were there, whether there was a drop in the number of degrees of freedom, therefore less radiation pressure that to prevent collapse, and so on. It's difficult otherwise. But I would say that would be one way. No? Imagine that there is more degrees of freedom beyond the electroweak scale. So at 10 to the, let's say 100 TeV. Let's just put an example. This would correspond to 10 to the minus 10 solar mass black holes. So if you see that there is a clear decrement at that time, and you see a large population of 10 to the minus 10 solar mass black holes, you might infer from there that not only are there new degrees of freedom, but well, they would contribute to the physics of the expansion of the universe at the time.
So I guess what you're saying is, so I guess
100 TeV, nothing more.
So I guess what we're saying is, if you can get a primordial black hole mass spectrum to know what the degrees of freedom are, or you can also do it with the cosmic spring spectrum, and then you also use Carlos Tamarit's mechanism for getting the maximum reheating temperature from delta N effective. Maybe you can, because of course Carlos's mechanism had a sensitivity to G star. I don't know how strong that sensitivity was. Then yeah, maybe combined either through a string or PBH mass spectrum. You could really,
but that doesn't take you very far away. I mean, it's 100 TeV. You keep on raising your energy, say 10 to the 5 GeV and so on, and then the size of the black holes would be so small that, according to a standard emission of Hawking radiation, they would have evaporated by today. Unless there are new phenomena. Geert Valley has been speculating about this. I listened to him on a very interesting talk, that there might be remnants due to unknown laws, quantum mechanical laws of black hole evaporation. If this happens, then there might be remnants up there of masses below those that you would expect to see today due to evaporation, so below 10 to the 15 grams. And then you would be able to probe such scales. But I cannot qualify whether Giat Valley's ideas are correct.
So I suppose the CVO limited and effective. I've only seen one calculation for it for the CVO limited, and it's by someone who's left the field, so I couldn't actually figure out how they did the calculation. But I suppose the CVO limited experiment there, that CMB constraint on ineffective. Yeah, I wonder if it's possible at all. It sounds like it might be very difficult to beat that at BBN.
Yeah, that's what I would say.
What is CBO? CBO is
a cosmic variance limit.
okay.
That's the limit.
Okay.
So there's a claim in the literature that you can get down to delta n effective of 10 to the minus 6, which will give you an omega of around about.
What scale? That depends on scale.
12.
What scale? You mean CMB scales?
Yeah, exactly. CMB scale.
Okay. Well, I think
But,
it's a one.
but
How, by CMB observations or how?
By CMB observations. It's by someone who's left the field, so I cannot vouch for the result.
I think that's a bit too far.
But the theoretical, so I mean, here's the problem. If you can do it experimentally, observationally, that's great. But at the moment, the theoretical uncertainties from the standard model itself are at 10 to the minus 3. This was the reason why we took the 10 to the minus 3 as a benchmark, so to say, because theoretically, the theoretical calculations, I mean, you can calculate this also theoretically, so to say, what you get from the standard model, and this is at 10 to the minus 3. So if it were possible observationally to go to 10 to the minus 6, then also the theorists have to sit down and to improve. They have to do higher order calculations and so on to.
Andreas, could you remind us, how do you get 10 to minus 3 in the standard model? So what's running in the loops?
I think Carlos looked into that.
Carlos. Hi, Carlos. Long time.
Hi there. Sorry.
Hi.
How do you get 10 to minus 3?
No, well, I mean, we didn't say that there's a model in which you get 10 to the minus 3. We saw that there's some claims that this could be a future sensitivity in a hypothetical future. So in the Line and Gigleri paper, they did, I think, mention a possible future sensitivity of 10 to the minus 3. So there was
10 to the minus 3 was also, this is the theoretical uncertainty.
Yeah,
yeah. I mean, this is, so to say, so everything beyond that would be, you have to improve. So if you take the standard model and to calculate, so delta NF is not 0 in the standard model. You have to define what delta NF means, yeah. and delta NF is 0.0 something in the standard model with an error bar. And this error bar you have to improve, so to say. Let
me clarify. Does that have to do with like what happens with the neutrinos? That they have a tail of neutrinos,
all these things, and
instead of being 3, it's 3.046. No, because you have this tail of neutrinos still.
And there is an error bar,
which can be described as if they were adding a little fraction of a degree of freedom to the relativistic species, right?
Indeed, okay. Indeed, and this has to be, if you want to, the theoretical prediction of this has to be improved if the observations start to get in this region. So if there are proposals to that observationally you can do it better to 10 to the minus 6. Then the theorists have to sit down. And
well, I can imagine, for instance, lepton number violation. If you have extra operators in your Lagrangian, which would contribute to the distribution function, the partition function of neutrinos and electrons, then of course they would be adding a little fraction of a degree to the relativistic species, to the expansion of the universe. Very tiny.
But I imagine it's easier to improve the theoretical sensitivity than it is to build a limited experiment.
Absolutely. But I would say 10 to the minus 3 is about the limit. I can't imagine going down 10 to the minus 6 with CMB experiments.
Yeah.
But it would be nice. If you could send us somehow the literature about that, or the citation where you found this number.
I mean, just put it in the chat window. I tried to chase down the author because there wasn't enough in the paper to understood.
Can you put it on Mattermost instead of the chat here?
Yeah.
Because then it's there forever.
So you said that this bound comes from brief ranges, or what? I didn't understand.
So this is a hypothetical CVL limited experiment. And unfortunately, the author left the field. The author did the calculation left the field because I did try and get some information on it. They did send some brief, a brief explanation needed to put there, which I think is okay to put in the Dropbox. It doesn't look like there's anything private in here. It's just like the information you need to do the calculation, like the parameters I use. So I'm going to also put that in the chat.
Okay, thank you. Any other question?
That's information. I mean, it's a if it's correct, that means you could get to omega gravitational wave of 10⁻12, which would be huge for any high frequency source, of course, as well as the heating temperature. But obviously, we don't know whether that's trustworthy, that result.
Yeah.
So I have a question, maybe to Andreas, I guess, and that is kind of, or also Axel. Axel's also here, kind of regarding the kind of the potential of what we could do with an ALPS type experiment, like what frequency, because as I understand correctly, like kind of at the moment, the frequency range that you're sensitive to is essentially limited by the specific type of camera that you're using, by the photo detector.
And also by the beam pipe. The beam pipe is very small, and this means you get effects from the beam pipe, which affect, so to say, the velocity, so to say, of the photons, or the phase velocity, and therefore we have a cutoff. I think this we have derived in our paper with the Big Bang thermometer. I think it was at 10 to the 12 hertz. So we have to go up only above 10 to the 12 hertz. So so ALPS cannot be used for the cosmic to look for the cosmic gravitational microwave background, but above that we could take any kind of detector and will be sensitive then in this region. So if some experimentalist says I have a sharp signal at 10 to the 13 hertz, we would have just to put a detector which is sensitive at 10 to the 13 hertz instead of the one which we have now. It's in the optical range, so at 10 to the 14 or something. So
but should say that with the cavities, no?
With the
then the sensitivity is of course limited by the bandwidth of the cavity.
So you lose, you lose automatically. So this for the a square root from the so you lose the sensitivity if you go away from the 10 to the 13 hertz where we have the cavity. You go away, you lose 2 orders of magnitude in sensitivity, just because you cannot. We don't have a cavity at this range.
So what would I need to do if I want to say I want to go below 10 to the 12 hertz and say you had an arbitrary amount of funding?
10 to the 12 hertz. I mean, you have to increase. So we said we have to use something which has large B times L times square root of A. So just you have a big volume, big magnetized volume, and long. So I mean, so therefore you saw it immediately. So if you had taken as a magnetic conversion volume, you take IAXO or baby IAXO, you have better sensitivity, so to say.
But is there any fundamental, because in your paper with Carlos, you had this sensitivity curves like prospects for Yaxo and baby Yaxo maybe and other experiments.
We just put it so there was no reason why we put it exactly so we were putting it, of course, exactly at the maximum which you get from the cosmic gravitational microwave background.
Yeah.
And this is, but there is no. Because this was a paper about the cosmic gravitational microwave background, and we know for that we know exactly where it peaks. I mean, so and
No, but I wanted to ask, so with this technology of magnetic conversion, is there any fundamental reason why building a bigger experiment without any bounds on the fundings, we cannot go down to the BBN bound?
I don't think so, but
okay. So in principle, building a huge
magnet, yeah. So I mean, now already with MagMax, this will be the largest ever built magnetic field volume with magnetic field. So which is 1 cubic meter.
I think it's important to point this out, no, because we don't know. Maybe at some point we will get enough fundings that we can build a big experiments on this and go down to the BBN.
I think it's really the issue as Anna was mentioned with the magnetic field. So MagMax will be the largest dipole ever. And so it's not just about funding, it's also about safety. You store lots of megajoules inside the magnetic field. And no one knows what happens if you go even to gigajoules, for example, stored energy, then it becomes really delicate to operate such a thing.
Okay. Yeah, that's why I was asking whether there is any fundamental or reason or something like that. Yeah, Mike, you wanted to add?
Yeah, you asked me some while ago to do a calculation of what would be needed in scale, and I've done that, and it looks as though you'd get down to the BBN limit. I think if it was something like 170 kilometers long.
So it still fits
something like 10 Tesla field all the way along it. So you're getting into really quite large facilities, I think.
Yeah. Okay.
Which frequency are we talking about now? Because this also must depend on the frequency, right?
Yeah. So I'm talking about a few gigahertz.
But then it must also be, in order to avoid this losing the conversion, it must be also quite a big range.
Yeah, absolutely.
Yeah.
Okay, we have to think something else. Okay, any other question or comment or whatever you like to discuss?
I would like, maybe just spontaneously, but I would like that we also think about usage of existing facilities like Alps and others, where we can have maybe some quick experimental results on search for gravitational waves. And therefore, of course, it's very important that the theory does not exclude that parameter space. It's reasonable to look there in some sense, like, for example, the black hole mergers asteroid scale, which we have been discussing yesterday. But I think for the field, it would be really good if we get some experimental papers out, just showing also results.
Yeah, of course.
Yeah. So
and there's a lot of blank space, of course, when we look, and of course, but as you said, we should have at least a target. We should look in a frequency range. It would be, of course, if you do it. If you do it automatically, then you don't. Then you do it anyway. Yeah, but it would be.
Talking about filling the gaps, I want to advertise here that we work with Hitoshi Murayama and Graham White, who's present here, on filling the gap between PTA and LISA with Gaia and in the future Theia. So looking for motions of stars in the galaxy and looking for correlations in their positions. If you have a stochastic gravitational background which move coherently all of those stars, then you should in principle be able to tell that they're there. And this would fill up at a sensitivity similar to PTA, actually even better than PTA, closer to SKA, all the way to LISA. And this, I think it's an interesting window which still remain. Of course, it's very low frequency. No? We're talking about microhertz rather than megahertz or gigahertz. But those holes are beginning to be filled.
There is Vale with the hands up.
Yeah, but it's a new topic, so I was, but yeah, so I was just because like one of the things we discussed yesterday was the coherence length question, right? And then Danny posted on Mattermost last night that essentially for gravitational waves, if I understand correctly, kind of sourced like at temperatures of essentially a gut scale and kind of our horizon size or close to horizon size at sourcing. That then kind of the correlation length in time, just from the fact that you're looking at different patches, is something like super tiny, like 10 to minus 10 seconds or so, which then if you translate to spatial dimension, right, is something like centimeters, right? So, and this is, and like, I think typically kind of gut scale temperature should correspond to megahertz waves today. So this really, I think, if this would really, I think, show that there's, I mean, as we were suspecting yesterday, right, that the coherence length of these frequencies is really tiny, and you can really not hope to kind of have cross correlation in neighboring detectors.
Good point. Maybe Mike wanted to say something about the sources at very high frequencies. I saw you appearing.
Well, just I think following up the comments that Axel and Andreas made, one of the problems we're having is that we've got so many theories and they are guiding us into our expectations. Whereas if you took a very purist experimental point of view, you would say, hey, this is an area that's completely unexplored. And, you know, the history of electromagnetic astronomy is all about, you know, building a telescope and then saying, wow, look at that out there. You know, we didn't know what that was. And the theorists, excuse me, I know there are lots of theorists listening, but the theorists then
I'm a hardcore theorist, and this is music to my ears. This is my
with me.
Well, the theorists pile in afterwards and explain what a pulsar was.
We'll explain it, but
they were noticeably absent in the years before pulsars were discovered. So you know, the trouble is you can't base a really good funding application on just the basis that, oh, we might discover something. But we should keep that in mind and not constrain ourselves too much, I think.
Yeah, very good point. Can you, Axel and Andreas, comment a bit more on the plans of DESY concerning microcavities? Microwave cavities.
Microwave cavities.
Yes.
So we are. So I think so. We have a study group within our high energy part of DESY, and we are studying different possibilities, and one of them are the microwave cavities or superconducting RF cavities, and but there is nothing. So we are just studying this without having consulted the other part of DESY, which is the machine division, the M division, which is using and developing these kind of cavities. So we had common seminars, but there is not. So at the moment there is no activity. So we are following this, and we are trying to get an opinion within the high energy department what to do, whether we want to, whether and where we want to engage in high frequency gravitational waves, but this not there's nothing decided yet. So so this is probably. So Axel, maybe you can also.
No, Andreas, cannot add, but just maybe comment in addition that some time ago, last year, we tried to get the accelerator division, the expert on the cavities, a little bit engaged in axial dark matter search based on cavities, which is also a nice additional feature for baby AXO, for example. But due to their overload in hardcore accelerator business, XFL, Flash, and Petra 4, they just didn't find time. So therefore, I'm also a little bit pessimistic, even if we agree that it would be a nice road to follow. I probably will not see any concrete steps in 22. This might need some longer time to free resources and get people working on this.
I think there are so I have the impression this was like in the beginning of our Axion activities at DESY. So the people in this division, they are very much interested in such things. But of course their bosses are saying you should first. So first we have our everyday business, which has been agreed and which is the main task of DESY, and we have to see when we can whether we want to engage in the other things. So you can do it maybe. So at the beginning, sometimes people are working in their free time for us, but of course at some point this has to change. And with Alps it was in the beginning, so Axel was doing it in his free time, so to say, and so it takes.
And also, if we so we don't write minutes, but of course it's recorded. But for this, it's also important always if how the external community is reacting on this.
Yeah, it's very important. So
very crucial. So if you start pressuring us, it would be very helpful.
Yeah, no, this is very helpful because, of course, it's always if you are in a place they say, oh, the Ringwald or Axel, they are always they have so this is their private business or their private things. But if from outside some people are coming, oh, you have these magnets. If somebody from Max Planck is coming and say, oh, you are running this magnet and so on, can't you do something? Can't we put an Axion experiment there and so on? Then they suddenly, the directorate says, oh, that's interesting. So Max Planck wants to enter here and so, and then so this is yeah. So this helps very much. So if there's a community coming from outside and saying, oh, so we have so DESY should be a hub for gravitational wave new gravitational wave experiments. Then sometimes then it could be so that the thing flies much earlier than if Axel and myself are saying, oh, that would be interesting, and we convince some people there, and then they say, okay, this is your hobby. I mean, this is it's of course, yeah.
Okay, good. We will have time during the discussion sessions to keep talking about this. Now, let me